Okay, so my presentation is mapping the Milky Way with cross-sectional graphs.
So Felicia, can you we can't hear you, Felicia. I don't know what's going on here.
Make sure
Oh,
the speaker is turned up.
It may also be
Nathan, we're
my
hearing her fine over here.
me.
Can
It was
It is your
working.
fault.
can you hear me now?
There we go. Now we got you. It was Bob's
Oh,
fault.
okay.
Definitely wasn't mine.
Okay.
Okay, please. Sorry.
Um, so my presentation is mapping the Milky Way with cross-section graphs. Um, so we see the galaxy as a strip of, oh, sorry, let me move. As a strip of stars, but what does it look like in 3D? And we can use radio astronomy to figure out more information of its 3D shape, such as like the distance of the hydrogen clouds and the galactic arms. Um, so we use the little Thomson Observatory 15 dish antenna to collect data on several different longitudinal galactic degrees. The simple procedure is to collect data from hydrogen and then refine the data and then calculate the distance of the hydrogen clouds by its velocity and then analyze the graphs. So some background information of the galaxy and our position is that we are 2/3 of the way from the galactic center, and the Earth orbits around the sun at a 60 degrees angle from the plane of the galaxy. So we see the Milky Way as a circular band around the Earth, but we may not always be able to see um, every degree, every longitudinal degrees of the galaxy for different seasons and different hemispheres. The longitudinal degrees that I've been talking about is the theta shown here. So if this is the center of the galaxy and the yellow dot is the sun, the theta would be the degrees of longitudinal the longitudinal degrees from the center of the galaxy. And the latitude, galactic latitude, would be the degrees above and below the plane of the galaxy. So what is it that we are detecting in our galaxy to figure out its shape? We're detecting the hydrogen because 73% of the visible mass in our galaxy is the hydrogen. So that means if we detect where the hydrogen are, we could basically know where most of the mass of our galaxy is. And hydrogen has this property where if it has a proton and an electron, and they both have a spin. And when the electrons originally that spins the same way as the proton switches its spin to where it's spinning the opposite direction from the proton, it emits a wavelength of 21 centimeters or 1420 megahertz. And this is a radio wave that could pass through the atmosphere of the Earth, and it would make it really convenient for us to detect on, like, for amateurs or anybody to detect on right on the ground of Earth. um, the next step is cleaning the data that we got from the hydrogen in the sky. Um, we use a low noise amplifier that attaches to the LTO-15 telescope so that we can amplify the signals that we get from the sky and retain more information. But it also serves as a really good reference for our data that we collected, because the amplifier is in the same environment as the telescope. So if we instruct the antenna to look at the sky and then look at the resistor of the amplifier, we could use the data from the resistor as a reference sample from the data from the sky. And by alternating the signals back and forth, every data sample would have a reference sample from the resistor to compare with. And that could filter out some of the environmental factors, such as noise from cars or cell phones, or machine efficiency from the weather. For example, when the weather is colder, the antenna would work better, but so would the resistor be cooler, and it would serve as a reference to filter out some of that noise. Another part of cleaning our data would be, or refining our data would be, taking out some of the outliers we usually figure out the outliers by turning our data into percentage values, and the data with the highest energy that we detected would be 100%, and every other sample would be relative to that sample data. So if we find a data sample that is unexpectedly low, or one data sample that is unexpectedly high, and the rest of the sample, the values are at really low percentages, or all at really high percentages, we would know which samples to take out. For example, this one, sample 128 has 0%, but like most of the rest of the samples have around 80, then that would be a really obvious outlier for us to take out. We also sometimes use the change in values of neighboring samples. For example, if neighboring samples are all at a relatively low energy, and then one sample is all of a sudden really high, it would have a really large change in percentage, and we would know to take that sample out. And after taking out the outliers, we could adjust the data from the Doppler effect due to the velocity of our own solar system and the velocity of Earth rotating around the sun, and the rotation of Earth itself. To figure out the distance of the hydrogen clouds from the galactic center, we would have to use we would have to figure out the hydrogen clouds that are traveling the fastest away from us, because we know those hydrogens are traveling along our line of sight. And in every hydrogen that we see would have different velocities, because some hydrogens aren't traveling along the line of sight and some are. And using the relativity of these velocities, we could figure out where the different hydrogen clouds would be. And we could find the hydrogens that are traveling away from us the most by figuring out from our sample which bunch of data have the lowest frequency, because traveling away from us means that their frequency would decrease because due to Doppler effect. This leads to another sort of subject about dark matter, because Kepler's laws tells us that objects orbiting in space further from the center should have lower velocity and vice versa. But our data showed that the velocities of the hydrogen clouds at any distance from the galactic center were about the same. And that means for every longitudinal data that we've collected, our line of sight would correspond to a radius. Our line of sight would correspond to hydrogen clouds that are traveling away from us at different radiuses. But these hydrogen clouds are all traveling away from us at about the same speed, which is very weird, because that means that would only happen if there is some sort of dark matter that is making the whole galaxy heavier, but we can't see or detect it at all. However, this phenomenon allows us to assume that every hydrogen cloud, their true velocity is around the same as our own velocity, which is a known value. And we could use this value to do trigonometry to figure out the actual distances of these hydrogens from the galactic center. And doing so would result in these sorts of graphs where the yellow dot is the position of the sun, and the fan thing is sort of like from the sun we collect data at a certain longitude, but above and below the galactic plane. So these samples are mostly plus or minus 10 galactic latitude at a certain galactic longitude, and the galactic longitude is signified up here in it is the number after LTO 15P. And this is sort of just a gift to show how our samples sort of varied from increasing galactic longitude. Here is a still image of some of the most important data samples that we collected. As you can see, the galactic longitude that is more near the 0th degree, which is the center of the galaxy, are brighter and have higher energy levels, and they look sort of funny in like a curvy shape because these samples are magnified, because originally they are plus or minus 10 degrees latitude, but in order for us to see better, we magnified it. But this causes like a fan shape, which sort of makes it hard to interpret, but at least we know that the hydrogens near the center are brighter. And that makes sense because near the center there should be more mass. But we also noticed that near the center there is a very weird hole of nothing, like pitch black, not even purple. And we think that's the actual galactic center, which all of the hydrogens are so they're so energized that they don't have any electrons anymore for it to like flip around. Basically, they're like plasma. and that way you wouldn't be able to detect any radio waves coming from the center of the galaxy. But from these graphs, you could still tell that the other galactic arms that we detected, they fluctuate up and down from the 0th degree line of the galactic latitude. For example, 40 degrees, the smaller galactic arm is sort of above the 0th degree line, but here in 90 degrees, some of the dots are lower, which means the galactic arms sometimes are above and sometimes are below the galactic line. And this shows that the galaxy is actually warped instead of just a plain flat surface. Here is the data that is not magnified. It is pretty hard to see, so I guess that's why we magnified it. But we could see that like most of these data are sort of circular, which would mean that our galactic arms are mainly circular arms, but they fluctuate up and below the galactic the 0th degree galactic latitude. And our conclusion is that the galaxy is warped, and our data matches the data from NASA, which showed that some of these arms are farther away and are in sort of like a spiral shape. Because from our data, we could see that these galactic arms are sort of coming closer and closer to our position, because the warp shaped is sort of the warp shape is like, as you increases the galactic longitude, the arms gets closer to our position. And our data shows that the distance that we detected where the hydrogen clouds are similar to where NASA detected their hydrogen clouds, which makes our data more credible, I guess. We also showed that the position of our sun is not in the main galactic arm, and this is a very important part for our survival, I guess, because if we're in a place where too much stars and too much stuff, it's gonna be a lot harder for us to maintain a stable environment on Earth. And we also showed that in our data, where there isn't much brightness around the sun until we get really close to 90 degrees, which we're detecting the stars right beside us. And that also fits with the data from NASA, which we were very happy about. These are some of the references and some of the, I guess, research paper that we based our research and project on. And I would like to acknowledge my mentors, Ted Klein, for helping me most of the way, and as well as Jay for inviting me to this conference, and Miss Domenico, which is my high school teacher, for organizing and running the STEM program so I could do this project. And is there any questions?
Any questions from our group? So, are you planning on continuing any further studies? Using TED software or other software to research the distribution of neutral hydrogen in the galaxy?
I think I might do research on maybe physics or astronomy, but I think I would probably move on as I sort of like go to college and take different classes on different physics subjects.
What are you able with this software, are you able to determine any differences? Do you see any differences in the velocity as you get away from longitude 0, as you get higher and lower from the galactic plane? Or does it seem to be pretty steady no matter which part of the galaxy you're looking at?
The velocity is mostly the same. Well, I think it's pretty stable. Like if you're only talking about above and below the above and below the galactic
Galactic
plane.
Yep.
Yeah, the galactic plane. Because uh because the distance is sort of, or the we would assume that the velocity is the same for almost like all mass in the galaxy, but the difference of velocity would be meaning like the distance away from the galactic center. And here we could see like these these bundles of hydrogen clouds, they're sort of mostly circular, except the ones that are skewed. And I think that means that the distance is the distance that we calculated, like they're pretty stable. They're just one clump together, and they're all sort of traveling at the same speed, or not the same. They're sort of at the same distance, but just above and below the galactic plane. Because we sort of use the speed um, as determining like how far it is from the sun.
Mhm.
And this is sort of an assumption, but like we didn't really use the speed as sort of a part of the data collection. We use it as sort of an assumption to determine the distance of the sun, from the sun.
Ed?
Yeah, I have a question. First off, I want to say that this is quite a good demonstration of the capabilities of small telescopes, radio telescopes. But I did want to understand why you chose to do longitude 20 through longitude 90. I think there's like 360 degrees of longitude there.
Yes, partially because the some of the as I tried to explain in the beginning, some parts of the galaxy is hard to see at certain seasons, and I did this in the fall with my mentor, so some of the galaxy was not able to be seen at that time. And yeah, and some of the other reason is because of the math, the trigonometry that we used here. Oh, so if our angle of line of sight, like if that angle exceeds 90 degrees, it would be hard to use the same method of math to determine its velocity. We would need to use like another algorithm in the data set. I mean, in the program.
That's perfect. That explains it very well. Thank you.
I'd like to,
Yes, sir.
I wonder how close to the sun, when you're, aiming your telescope, how close to the sun can you get before the sun begins to interfere with your measurements.
Oh, I
If she's
I
using
actually
Yo, I bet Ted probably made sure that she was just far enough away,
Ah,
if I had to guess.
yeah, we didn't. I don't think we tried because I was usually at school while while the data collection was going on, but like I don't think we would like aim our telescope near the sun because the sun is basically just a really bright hydrogen blob.
That's great.
So yeah, I guess we would just wait until like midnight or sometimes during the school that is we would aim it at a place that is not where the sun is at, I guess.
Okay. Anything else? All right, thank you very much. Excellent presentation.
Thank you, Felicia.
Thank you.